In 5.5, or in the textbook 5-5, we're going to go over multiple angle and product of sum identities, but in this video, we're mainly going to focus on just multiple angle identities. Not going to worry about product of sum, just multiple angle identities. Now, the first part of multiple angle identities, we're going to go over double angle identities. What I mean by double angles is you have two of the same measure of the angles, so two angles of the same measure just being combined. So if you were to see x plus x, you can simplify that into 2x. If you have m plus m, you simplify that to 2m. If you have 2f, f plus f, you can combine that as 2f. So it's just basically rewriting into a shorter, easier version. So when you're looking at these identities, you see that when you have 2 theta, that means it was just theta plus theta. So two angles of the same measure just being combined together, but in a shorter version. The first identity is sine of 2 theta is equal to 2 times sine of theta times cosine of theta, or simply 2 sine theta cosine theta. The second one, tangent of 2 theta is equal to 2 times theta over 1 minus tangent squared theta. Now, the last three, they're all for cosine of 2 theta. Now, the first one, cosine of 2 theta is equal to cosine squared theta minus sine squared theta. The second one is cosine 2 theta is equal to 2 times cosine squared theta minus 1, or 2 cosine squared theta minus 1, if you were to say that quickly. The last one, cosine of 2 theta is equal to 1 minus 2 times sine squared of theta, or 1 minus 2 sine squared theta, if you were to say that quickly. Now, the reason there's three of them is because cosine of 2 theta can be written in different ways, and it can be beneficial or helpful depending on what kind of problem you have. So, and you won't be able to know until you see the problem in front of you, analyze, and determine which one is best to use. Now, all three of them can be used in the same given problem, but depending on which one you use, one might be using more steps while another one use less steps, depending on what kind of given problem you have. So you might have problem A where the first one may use 5 steps, while the second one use 10 steps. Or you might have problem B where the last one might use 3 steps, and the first one probably end up using 7 steps. You won't know until you actually look at the problem in front of you, analyze, determine which of the three is best to use so that it makes your work easier. So like I said, you won't know until you have the problem in front of you and determine which of the three for cosine 2 theta, which one makes your work easy to use, or which one is that saves you a lot of work, a lot of steps. Now below the identities, the proof, so it's proving double angle identity for sine, meaning how it works and how it came to be the identity sine 2 of theta. So below, sine 2 theta is equal to sine of theta plus theta. So that's, again, tying to what I said in the beginning, when you have two angles of the same measure just being combined. So like, for example, x plus x, that's the same thing as 2x. If you have m plus m, that's the same thing as 2m. If you have f plus f, it's the same thing as 2f. So when you have sine of theta plus theta, using the sine sum identity where angle alpha is equal to angle beta, which is equal to theta, it can be rewritten as sine theta cosine theta plus cosine theta sine theta. So basically that's the same thing as 2 sine theta cosine theta. Now, even though if you look closely between these two parts separated by the plus, even though they're in different order, multiplication, so sine theta times cosine theta, is still the same thing as cosine theta times sine theta. As I mentioned in class where I asked what is 4 times 3, that's 12, it's the same answer if it was 3 times 4. So again, 4 times 3 will give you the same answer as 3 times 4 because you multiply with the same numbers. The only thing different is the arrangement of the numbers. So the same thing with sine theta times cosine theta will give you the same answer if it was cosine theta times sine theta, which is why you have 2 sine theta cosine theta. It's the same thing as if you were to write it as 2 cosine theta sine theta. So that's how sine 2 theta is equal to 2 sine theta cosine theta. Now below is an example of how to apply the double angle identity. But this ties in to what we cover in 4.1 and 4.3. So again, 4.1 and 4.3. So in the example, the question is, if sine theta is equal to negative 7 over 25 on the interval of pi, comma, 3 pi over 2. That means in the third quadrant. Find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So reading the information here, since sine of theta is equal to y over r, so that's basically 4.1, is equal to negative 7 over 25 on the interval of pi, comma, 3 pi over 2. So 180 degrees to 270 degrees, or third quadrant. One point on the terminal side of theta has y-coordinate of negative 7 and a distance of 25 units from the origin. That means it's the r value. So r is 25. And remember, r is always positive. Regardless where it is, the value is always positive. Now the x and y can be negative. In this case, the y is negative 7. So the x-coordinate of this point is therefore negative square root of 25 squared minus 7 squared. Now, the reason it has a negative is because in quadrant 3, we already know that y is negative, but you gotta remember that x is negative. That's why you have a negative in the front of the square root. So when you simplify the square root of 25 squared minus 7 squared, it will become negative 24. Using this point, we find that cosine theta is equal to x over r, which again came from 4.1, or negative 24 over 25. Tangent theta is equal to y over x, again from 4.1, or 7 over 25. Now the reason it's positive is because negative 7 divided by negative 25, meaning negative divided by negative, it will simplify into a positive number. So it's going to talk about using these values and the double angle identities for sine and cosine to find sine of 2 theta and cosine 2 theta. Then find tangent 2 theta using either the tangent double angle identity or the definition of tangent. So again, the definition of tangent, that was from 4.1, meaning y over x, or you could also use the quotient identity from 5.1. So again, you could also use the quotient identity. All right. So the first one on the left side is the first double angle identity. So sine of 2 theta is equal to 2 times sine of theta cosine of theta. So from this given problem, for sine theta, that was from the example, sine theta is equal to negative 7 over 25, which is why you have it here. And then cosine theta is after you solve for it, so negative 24 over 25. So all you have to do is just basically 2 times negative 7 over 25 times negative 24 over 25, which will become 336 over 625. All you do is just multiply these angles straight across. That's all you do. And to find cosine 2 theta, basically using one of the identities, so 2 times cosine squared of theta minus 1. So all we do is just plug in cosine of theta. So it's going to be 2 times negative 24 over 25 squared minus 1. So just remember your PEMDAS. Do the square first, distribute the 2, and then subtract by 1. Now remember, when it's a fraction minus a whole number, got to work in fractions with common denominator. So for cosine 2 of theta, it will equal to 527 over 625. So basically the same work we had done since the beginning of the year, working with fractions, multiplying, using PEMDAS. All right, now, tangent 2 of theta. So in method 1 is using the identity that was mentioned before. So tangent of 2 theta equal to 2 times tangent of theta over 1 minus tangent squared of theta. So you're just going to basically plug in the value of tangent theta, which is 7 over 24. And then you're just going to work it out. On the top, you're going to multiply by 2. On the bottom, you're going to do 1 minus 7 over 24 squared. So remember, always follow your PEMDAS. Do the square first. And then when you work it out, it's going to be a fraction over fraction, just like before. Rewrite it as a division of fraction, and then write it as a multiplication of fraction. Once you do that, you will have 336 over 527. Now, method 2, it ties into the quotient identity. So, for example, tangent of theta is sine theta over cosine theta, or tangent of x is equal to sine x over cosine x. So the same thing can apply if it's tangent to theta. You can rewrite it using the quotient identity, sine 2 theta over cosine 2 theta. So if you have found the value for sine 2 theta and cosine 2 theta, then you just simply plug it in. And then since it's a fraction, divide by another fraction. You're going to write it as a division of fraction. And then change it to a multiplication of fraction. When you multiply and simplify, you're going to get 336 over 527. So either method works. Doesn't matter to me if you use the double angle identity for tangent to theta or you use the quotient identity. Doesn't matter to me as long as you do the work correctly and then get the correct answer. So even though this is one example, I'm going to do more example using the double angle identities to help give you a better understanding how to use the double angle identities.